There's this and there's this. Okay, really good. They're very quick indeed. They really are very quick indeed. Well, the first one is quick indeed. Okay, the first one is following. And I don't know this, but let's back to the first, so I'll read it. Okay, this is the traditional example that we've seen a million of about chess set problems, and that's how we started in progress. But this is about producing three different products. So obviously there's a decision variable for each of them, and you need to, and there's a profit on them, and you need certain resources for each of them, and there's only a limited availability of those resources. So I don't I'm not going to go into on the basic formulation. So of course, here in the min-max, the decision variables are clear. They're just x1, x2, x3. So that's the amount of p1, p2, p3 to produce. Effectively, and then the constraints are clear. So when you look at x, you need 0.1, 1 is 0.1, 2 is 0.15, 3, and that can be more than 1.5, and you need 0.2 or 1 for the y resource. So that's equal to 13.5, and finally 0.2 up to 1, 0.2, 0.3, 9, and all this is right. Okay, so that's easy. Okay, this is the standard thing that we've been doing for you. Okay, now the legend is telling you that the government are either going to change some taxes or not, and you don't know whether they're going to do it or not. And depending on whether they do it or not, the profit of each of these products is different. So what it says there is, last sentence in this one says that you want a guaranteed profit to be maximum. Okay? So guaranteed in the sense that no matter whether they change the taxes or not, you still want the profit to be good. Oh, by the way, to register that, you make a half. Make a half. If you don't know how to draw a half, which I do, you can make a star. Okay. Where was I? Oh, so is the question clear? Okay, the profit is either going to be 30x1 plus 40x2 plus 45x3, or it's going to be 37x1 plus 30x2 plus 40x3. Well, you don't know which. But you want, in either case, to do well. So it's called min-max because that's what you need. So the objective is to maximize the smaller of the two profits. So the profit is either going to be 30x1 plus 40x2 plus 45x3, or it's going to be 37x1 plus 30x2 plus 40x2. Okay, and you want the minimum of these two numbers to be as large as possible. Are you with me? Yeah. But it's not a linear. It's not a linear function definitely because that's going to be some kind of will break in some points. So, so it's not a linear program like this. So what we're doing is we're learning a trick to make it a linear. Okay. Trick is we put a new decision variable there. Hey. Okay, what do we do with the new decision value? Is doesn't know. Oh, we want this A to be the guarantee on the profit we're making. Okay, so we want look at these two profits. We want the 30x1 is 40x2 is 45x3 B greater than or equal to A. And we also want the other possible profit to be greater than or equal to A. Plus AB plus yes, yes. Of course, it's just an example, but you get the general idea. That will work whenever your objective is to maximize the minimum of some things, or if it's to minimize the maximum of the things. So actually, the LP objective is now linear. In decision variables is to maximize A. Electric process is in So who thinks this makes sense? Who's quite unsure? Exactly as you're saying, we want to maximize the worst possible outcome. So no matter which of these two options happens, we're still guaranteed to earn at least A. We'll possibly earn more, we don't know. But at least this is what is guaranteed no matter which of the scenarios happens. In 2 weeks' time, we're going to start a very basic introduction to game theory. And there, things like this happen. We're trying to make sure that no matter what the opponent does, you're doing at least right. We're trying to make the least possible gain as large as possible. And one of the cases that we're looking at, it will lead to things like this, so maximizing the minimum of something or minimizing the maximum of some things. And there indeed we will then, like the linear formulation, that solves the game with easy workbooks. Any questions? Let's have a look at something that is very exciting. It's not in the handout. Does it remind you of anything? The reason it's not in the handout is because I only decided about 10 minutes to collect it. But it's very different. So I'm sure it reminds you of an assignment that you did in the first term, which it's about flow. So who doesn't remember what a flow is? Everybody remember what a flow is? Right. Remember, you want to volunteer what a flow is? Okay, so what is a flow? Oh no, that's not what a flow is at all. Okay, you have some sort of an interpretation in mind, what a flow could be in real life situation. But the mathematical definition of a flow is that it's a function that goes from the arcs of the graph to some numbers, right? Positive real numbers, right? Not real numbers. Okay? In other words, it gives you a function or a mapping is something that for each arc gives you a number. Okay, so think of a number sitting on each of the arcs. So in this picture that you see here, the flow is 0 everywhere. That's the second number, the number after the comma on each of these arcs. So it's a function that satisfies that. So it can't be negative. So in each of these arcs is greater than or equal to 0. It can't exceed the capacity of the arc. And okay, so this is a flow. We should have said that there's a flow from S to T. And T are some vertices. So you can see in the picture you have a node. You have a node S and a node T. And in every other node than S and T, you want the amount that's coming in to be equal to the amount that's going out. Because you can't generate. So the idea is that from S is like a spring. You're generating the flow of some liquid, and T is the target of the liquid, sink, disappearing, but in the middle of the network it can't disappear and can't be created. We're looking at flows that only have one source in one sink. Also flows. Thanks for this one. This is just a simple scenario. So what you want is that okay, so this sum here is overall arcs that n in a node V. This is the added all arcs that start in V, and you want this for all V. So the nodes are called V because they are called vertices. Other than S and T. So for every vertex other than a node other than S and T, you want that the sum of everything that's flowing in is the same as the sum of everything that's flowing out. Okay? That's very exciting. Because, why is it exciting? Because it looks like a linear constraint. So if these FAs were decision variables, which they are because we want to decide how much flow we can put on each of the arcs. And this is a linear constraint, right? And this is a linear constraint, and this is a non-negativity constraint. And what we want to find is a maximum flow. Maximum flow means that we want to maximize not over all A's, but the A's that start in S. Well, sometimes if there are some output end in S, then we want to subtract that. But in this example, there aren't any. Can you see how this looks like a linear program? Is that a linear program? Is it exciting? What? Okay. Backflows. What do you mean by backflows? These are one-way pipes. If you want two-way pipes, just draw them both ways. You treat them separately. Well, yes, but it's a different. Yeah. Good. So essentially, your question is whether we're looking at a maximum flow in directed graph or one which is inverted. We're looking at the direction. And that's the simple situation. And if you want to do an undirected one, then you can probably the best way to treat it is if the undirected edge is the best way to articulate Now it seems like you could put in something flowing there and you have flowing backwards, but in a basic optimal solution, that won't happen. Okay, so this is exciting. So now, what's the most exciting thing about this is something that we'll have a very brief look at. So it's just like it says that, and this is what we're going to teach, but what we're going to do next year, really, if you opt for the module. And it's called LP duality. Basically, the idea is that to every linear programming problem, there is a dual. And they both have the same objective, objective. But they don't at all look like each other. Completely different. One is to maximize something, the other one is to minimize something. The constraints are, well, kind of completely different. Not, of course, because they have to be somehow related. And it so happens that in the optimal solution, if they both have an optimal solution, then the objective is the same in both. There's a kind of a teaser. We're going to have a look at an example based on the chess set problem next week, and then probably, if there's enough time, also based on this, because when you dualize this linear programming problem, what you get is the minimum cut problem. And I'm sure you remember the minimum cut problem from classes. And there was a theorem which said that the value of the maximum flow is the same as the minimum cut capacity in a network like this. ring a bell? And in fact, which is it's mathematically very nice, it is a combinatorial theorem, which you saw in but it's also an instance of this duality of linear programming. Any questions about this? Or anything else? Why? Universe. Okay, so that's it for me. Enjoy the practice. And so.